Hello everyone, my name is Felix Rudolph from FGH in Aachen, Germany, and welcome to the presentation of the developed security-constrained optimal power flow for interconnected meshed AC and DC transmission systems within Work Package 2 of the Promotion project. First, something about myself. I studied business administration and electrical engineering at RWTH Aachen University and started working at FGH in Aachen in May 2017 as a research assistant. I did most of the company's research within Work Package 2 and 12. I will start with an introduction and motivation for the developed method, followed by the modeling and an overview of the whole process. Afterwards, I will show a performance evaluation of the optimization. In the end, a short summary and outlook are given. With the introduction of the meshed offshore system, the operational planning and system operations processes of the transmission systems operators will need an optimization method to evaluate preventive security principles in these meshed AC and DC systems, as it is mandatory today. In existing methods, the offshore wind farms with their point-to-point connections are considered as a unified generation unit connected to the onshore AC transmission system. Future meshed HVDC offshore systems are more complex than the radial connections and will offer more options in system operations. A consideration is therefore in more detail necessary. Existing methods are not sufficient for optimizing asynchronous but also interconnected meshed AC and DC systems for normal operation and in a contingency situation with preventive measures. It is therefore necessary to develop a security-constrained optimal power flow, or SCOP, for interconnected meshed AC and DC transmission systems, which will be able to fulfill these requirements and which will be presented in the following. The SCOP requires a steady-state modeling of the transmission system and the installed equipment. The most important models are therefore introduced on the slide. The generation units are limited by their minimal and maximal set points for the active and reactive power outputs. Renewables aren't that flexible because of their external weather dependence. They can only be curtailed. Furthermore, offshore wind farms are linked to their corresponding converter via a constraint to allow for simultaneous set point changes. The cables and lines of the systems are named branches in this method, and their thermal design limit is modeled with a maximum allowed current over the branch. The converters connect the AC and DC transmission system and are modeled as individual injections into the respective system, similar to a generation unit. They also have a minimal and maximal set point for their power output. Additionally, the sum of all converter set points per DC system has to be 0 at the moment, so they are lossless. To ensure the solvability even when a violation of the thermal design limits and therefore congestion still exists, slack variables are introduced. They extend the solution space to guarantee a solving of the optimization problem. Giving them high costs within the objective function ensures a minimal use in the result. The final optimization method consists of several modules. At first, all the relevant input data has to be loaded and processed. The next module is called outage approximation and assesses the fully meshed AC and DC systems during a contingency situation with a virtual power injection method. The result is an approximation of voltages and currents in the system during an outage. Outages that can be considered at the moment are the failure of AC or DC branches as well as of converters connecting the system. In the next module, the sensitivity calculation, the linearization of the nonlinear optimization problem occurs. With the information of the outage approximation, all the necessary sensitivities or power distribution factors are calculated. With all the information now available, the mathematical optimization problem is assembled with all the variables, constraints, and objective function. The objective is a minimization of the cost, therefore avoiding congestion in normal and contingency situations, as well as supplying enough energy for the existing load and avoiding as much curtailment as possible. As the optimization of the AC and DC systems occurs unified, fast results with convergence can be obtained. If for a reason the result does not converge, the determined resulting set points are taken back and the optimization starts again with a new outage approximation. In order to test the functionality of the developed SCOP, a performance evaluation with the well-known IEEE 118 bus system has been performed. The test system is modified with a meshed HVDC offshore system, containing 3 offshore wind farms and 1 additional reduced AC system, which is asynchronous to the rest of the grid. The initial power flow calculation has shown congestion in the AC and DC system, which can be seen in gray in the diagram on the right side. The outage approximation determined additional congestion in a contingency situation, which can be seen in blue in the diagram. After a run of the SCOP, the set points of various generation units and converters has changed, with minimal curtailment at 1 offshore wind farm. The congestions in both systems are completely dissolved, which can be seen in the diagram in yellow and orange. The utilization limit of AC branches is supposed to be at 80% utilization or below, and for DC branches at 100% or below. Both can be achieved within a few seconds. Performance evaluations on bigger systems have shown similar results. The SCOP is therefore working. I am now at the end of my presentation and will do a quick summary and outlook. In order to assess interconnected meshed AC and DC systems, a SCOP is necessary. For the method developed in this project, the AC and DC transmission system are modeled in steady state. To obtain the relevant system values in a contingency situation, an outage approximation considers outages of AC and DC components. The unified optimization is done in an iterative way for AC and DC in normal and contingency situations at the same time and leads to fast results. A performance evaluation with a modified IEEE test system has proven the functionality of the developed SCOP. Future development will include the specific analysis of curative measures, as especially HVDC systems with their power electronics will benefit from them. Thank you very much for your attention. If you have any questions, feel free to contact me.
Hello and welcome to the presentation of the RMS simulations of combined AC/DC systems. My name is Dimitri Nesterov. I am power system expert within Tractebel NG Impact. In this presentation, we will discuss about the motivation of the work, the methodology for planning phase of the MTDC grids, and we will end with a conclusion. A typical MTDC project is usually done in several phases. The first phase is usually the planning phase, followed by the detailed design, which is followed by the implementation, etc. The focus of this work will be on the planning phase, during which several key decisions have to be made, such as MTDC topology. This requires the analysis of the combined AC and DC systems behavior. Such analysis allows specification of the base requirements of the equipment. The question on how to investigate the behavior of the combined AC and DC systems arise. Electromagnetic type simulations are too computationally demanding for such studies. Also, some detailed parameters are required for EMT simulations, which might be not known at the planning phase. For these reasons, the use of phasor representation is attractive. This allows an average representation of the dynamics of both AC and DC systems, including the DC grid. This allows to simulate large combined AC and DC networks. The methodology for the planning phase of MTDC grids includes the following points. The set of criteria for steady-state operation is defined in accordance with AC and DC voltage ranges defined in Work Package 1. Then, the criteria for dynamic operation are set in terms of acceptable overshoots in voltage and currents and in terms of constraints on post-contingency states. Dynamic simulations are conducted and the performance of defined criteria is assessed. If needed, dynamic parameters such as control gains droops can be readjusted to meet criteria. In case criteria cannot be met, it is analyzed if the criteria can be relaxed, and if not, AC or DC grid reinforcement might be required. The test case, which was considered for this project, is composed of 3 MTDC networks running in parallel and interconnecting 3 AC areas, which are Nordic 44, Great Britain, and European systems. The considered operating conditions are normal operating condition and contingency operating condition. And the following 3 operating scenarios are analyzed: high wind, no power exchange through DC; medium wind, no power exchange through DC; low wind, high power exchange through DC. An example of load flow result is presented in this slide. For normal operation, it is possible to find a voltage range in which the equipment should be able to operate indefinitely. For contingency operation, it can be observed that some points respect defined voltage range, while others might require readjustment of control parameters or grid reinforcement. The transient behavior is analyzed in Eurostack software. Several tripping events were simulated, but only results of case 3, tripping of a DC branch resulting islanding of the MTDC grid, are presented in this slide. The results show the changes in the power flows of the lines as well as DC voltage variations. All simulations were found to be stable. The impact of the AC contingencies on the DC system was analyzed by simulating disturbance on the AC system. This slide presents the results for the AC case 2, 3-phase fault at the AC terminals of a VSC cleared after 100 milliseconds. It can be seen that the fault is seen in the main DC lines in the DC network, and the DC voltages also react to this event. The performed simulations were found to be stable. The impact of DC contingencies on AC systems was analyzed by simulating DC events. This slide presents the simulation of tripping of an MTDC network. It can be observed that the power flows in the healthy parallel MTDC networks are redistributed and are able to successfully stabilize the AC frequency. It can be concluded from the performed work that the RMS type tools allow simulation of large combined AC and DC systems within reasonable computation time and lower data requirement than EMT. The study provides indications regarding the normal and contingency operating conditions of the MTDC grid, such as assessment of the transient behavior at the system level, as well as the impact of AC contingencies on the DC system and impact of DC contingencies on AC systems. The studies provide also high-level recommendation for the design phase, but for the design of a particular equipment, detailed EMT studies are necessary. The studies can be used to define a set of control parameters such as DC voltage droop gains and VSC control tuning, etc. And the studies allow assessment of post-contingency operating points and transient response for the AC side. However, the DC system transient should be verified with accurate EMT model. Thank you for your attention. For further questions, please don't hesitate to contact me.